play with it in real time. Um, and we'll see where it goes from there. If you open up the link at the top, you'll see there's just a couple pages of material that I threw together, and then some links. And I thought maybe we'd just start right at the top on page two. It was one of the things I used to do. One of the things that got me interested in physics, really, of course, was math. I think everybody that comes to physics comes there from math because that's your first love. And I remember when the first programmable, not programmable even, when the first calculator came out, the HP 35. I thought it was really fun to just hit some keystrokes like sine, exponential, something. Just hit a few keystrokes, starting with a number, and then hit them again, and then hit them again, and then hit them again. And what I was doing was what would be called an iterative map, taking a function of x, putting some number in, taking the sign of that number, taking e to what I got when I got the sign of the number, and then getting a number back, and then taking that number, taking the sign of it, and the exponential of that, etc. I don't know if that actually does it. That probably doesn't converge to anything. But sometimes when you do that, you get sequences of numbers that converge. Sometimes they don't. Sometimes they diverge, and sometimes, as we'll see, they do some odd things. And this particular odd thing they do led ultimately to kind of an explosion of work in nonlinear dynamics, is called in physics, understanding that there was structure in what seemed to be chaotic kinds of, like turbulence, etc., chaotic things that happen in physics sometimes actually have a structure to them if you look deeply and if they're clean enough to be able to see that structure. So I should just start off with a little fun math here. If you just start on page two, I'm showing what's called the logistic map. It's a simple function. You take a number, you multiply the number by one minus that number. You take a number between 0 and 1, I should say, and you multiply that number by 1 minus that number, and then you multiply by some arbitrary parameter that is called r here in this case. So I'm showing there in the equation that I get a sequence of numbers, and the n plus first number in that sequence is obtained by taking the nth number in that sequence, multiplying it by 1 minus itself, and then multiplying by this parameter r. And a way of understanding the sequence, and I'm showing you a sequence there. For instance, if I choose r equal 2.81 and I start with x equal 0.2, so that the original value of x is 0.2, then I get the sequence of numbers that are shown in that table. And you can kind of see that it starts at 0.2, it goes up to 0.44, then up to 0.69, then down to 0.59, then back up to 0.67, then down to 0.61, and then up to 0.66, etc. It seems to kind of be oscillating between a couple of numbers. And I could go on forever, and we will. I have a spreadsheet that takes us out to 10,000 iterations, which we'll look at later and see what kind of things happen. But a way of thinking about what this thing is doing is shown in the graph there. And on the graph, I have plotted two functions. The straight line is just y equals x. And of course, that just means that if you take any number on the x-axis, you simply go up to that same number on the y-axis, and you plot all the values, and you just get a straight line with a slope of 1 that starts at 0, 0, and ends at 1, 1. I'm going to limit myself to numbers between 0 and 1 just because of the nature of the equation. That 1 minus x and that x suggests that I should keep numbers between 0 and 1. You can talk about what happens outside that, but you'll see it's uninteresting and or nonsense or explosive or something else. So we're going to stay between 0 and 1. So the straight line is y equals x. The curved line is the logistic map. It's just y equals r times x times 1 minus x. And for those of you that know, that's the kind of an inverted parabola. You can write that equation as r times the quantity x minus x squared. And the minus x squared, for those of you who may remember a little algebra, means that you expect to see this as a downward sloping parabola, a parabola that has a maximum rather than a minimum, which is the usual kind of thing you see. It should make sense because if you think about that equation, clearly when x equals 0, y is 0. Equally clearly, when x is 1, y is 0. The x and the 1 minus x ensure that when x is 0 or 1, you're going to get 0 out. But in between, you're going to get some positive number, and there's going to be a maximum. If it starts at 0 and ends at 0, and it's positive everywhere in between, which you can quickly convince yourself it is, then there must be a maximum somewhere. And of course, that's the nature of an inverted parabola, to have that maximum. So I'm just showing you what this looks like at this arbitrary value of r equal 2.81. And then a way to think about the iteration is to start at point 2. You see the red line going up from point 2. It goes up to the function. At that place, of course, the y value at that place is just the first returned value. That's what you get when you multiply 2.81 times 0.2 times 1 minus 0.2. And what you get is 0.4496, as is shown in the table there. So you see that that's how you get your first value. Well, how do you get your second value? Well, you want to put that 0.4496 back into the function. And so you want to go down to the x-axis and put 0.4496 in. And the easy way to do that is just to draw that first red horizontal line from the place where the first vertical hit the function, draw it over to the y equal x line, and now you are at x equal 0.4496, and you can just draw another vertical red line up to the function. And so one way of thinking about this sequence is just this what you're doing. You start somewhere, you go to the function, then you go over to the y equal x line, then you go to the function again, then you go to the y equal x line, then you go to the function again, et cetera, et cetera, et cetera. And if you do that in this particular case, you see that what happens after the first few iterations is you start actually spiraling in on a fixed point right there, somewhere around 0.65, 0.64, something like that. I haven't taken it out far enough to see. But you also see how you're going to go kind of above 0.64, then below 0.64, then above, then below. But it does converge to 0.64. And that's kind of the important thing here, is that's what this sequence will eventually converge to a fixed point. And in the language of dynamics, that fixed point is called an attractor. Eventually, if we continue this thing for too long, we'll talk about strange attractors. But for now, just talk about an attractor. An attractor is a place that a dynamic system eventually ends up at, if it ends up anywhere. So if you go to, let me just stop there for a moment to see if there's any particular questions on this. We're not going to do too much more than this today. I'm going to show you some more dynamic examples of it. We're going to look at a couple of videos, but that's about it. I did want this to be more informal even than normal, so let me try to stop and invite anybody up on stage. Hanson in particular, I don't know what your...
How detailed do you want to go on this? Because this is
do whatever you
completely
want.
non-trivial. I used to teach this stuff like 3 years ago, and I always had a notepad in my hand because it's not trivial. The fact that this converges to some place is completely non-trivial. There are many conditions on the derivative and the second derivative and so on and so forth. bottom line is some fixed points like this are attractive, meaning if you start anywhere, you will get to that no matter what. It's just a matter of time. Whereas some other fixed points are not attractive, in which case you have to hit the exact point to hit the zero. Else, if you
Right.
start even 0 plus epsilon, it will converge somewhere else.
Right. Yeah, and I think it's pretty easy to see. One of the important things you mentioned there. If that one of the reasons that you have the fixed point here is because of the fact that the function crosses the line, crosses the y equal x line, in a kind of a shallow fashion. If you imagine the function crossing much steeper, if the function crossed the y equal x line much more steeply, you might be able to convince yourself that rather than spiraling in on the fixed point, it would spiral away from the fixed point. And I think I'm sure that's the kind of thing you were referring to,
Yeah, something
Shamash.
like that. Exactly, exactly.
Yeah, and we'll see that we'll see that happening. In fact, as we go
Yeah,
on as well.
actually, that's very important. Basically, it's the derivative. If it is absolute value is less than one, um, it will guarantee to converge, and if it is greater than one, then it will diverge.
Right. There's this logistic map when you people started looking at it, and we'll see. We are going to just scratch the surface of this thing. The mathematics involved in the analysis of what happens at various values of that parameter r is just completely fascinating. We could talk about it for the next year and not have completed the results, but it's just the beginning of nonlinear dynamics, and we won't go into that kind of depth. But if you look at, I do have a link to the Wikipedia page on this, and you'll get a taste of just how much fascinating math there is involved in the analysis of this thing, if you look at that. Yeah. Any other comments?
The other part, there's the another kind of related thing is a very useful thing is the Newton method, and there actually you can have rather than the one derivative, first derivative, but if the second derivative is convex, then you're fine. So yeah, just want to mention that.
It's hard to, yeah, some of these concepts are hard enough even with your visuals. That's why it's going to be a challenge, I guess, to deal with some of these things without a lot. So one of the reasons I don't really have anything for you very very well developed today is just because I didn't even know how to get started. And I just thought, well, let's just scratch the surface and see what happens. Let's move on to slide 3, where I just show you exactly what I showed you on slide 2, but for 3 other values of r. So you'll see 2.81 up there in the upper right. That's the one we just talked about. But if we think about what happens in other values, for instance, let's just start with the upper left, r equal 1.18. At a small value of r, it turns out, in fact, I should have started below that. You might even be able to see that if I start with a value of r, and I'll just tell you this, if you start with a value of r less than 1, then this process of going up to the function, over to y equal x, to the function, to y equal x, to the function, to the y equal x, simply takes you down to 0. So with an r value less than 1, the sequence simply dies out to 0. That's it. The fixed point is 0. That's the only place where the function and the y equal x are the same, and that's what you get. With r equal 1.18, there is, although you can barely see it in the graph, especially if you're looking on a phone, there is actually an intersection, and that intersection is around 0.16, somewhere around 0.16. And what happens, you really can't see it unless you were to blow that up, is that the process of iteration just takes you to y equals x, down to the function, to y equals x, down to the function, and you simply converge very quickly to something like to that 0.16. Oh, I guess I should, did I say that right? Yeah, yeah, whatever that is, to that fixed point at 0.16. So that's all you get there. At 1.97, it's a little more interesting because you can see it a little bit better. The fixed point now has moved up. The crossing point of the function in y equal x has moved up to something more like 0.5, a little less than 0.5. And you can see the sequence there. You can see the sequence driven out. It starts at 0.2, goes up, 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 and starts slowing down as it gets. In fact, you can already see it's almost surely going to be something like 0.492387 something, because it's already converged. Those numbers have converged very quickly to 5 or 6 digit accuracy after just 8 iterations. So this is an example of an R value which will lead you to the fixed point, to the attractor very, very quickly. And then, of course, we see the 2.81 that we saw before. Oh, I should have. I'm sorry that I didn't. I thought I had included one other. Well, we'll see it. We'll see it when we start looking at the spreadsheet. That we saw what we got at 2.81. It's amazing that very quickly after 2.81, you get a graph like the one below. R equal 3.9, you're into what's called the chaotic region. It turns out that in this case, the sequence never settles down. You put in 0.2, you will never again get 0.2. This sequence will go on forever. You'll get not all values. You won't get any given value, but you will never get the same value twice. As long as you iterate this function, you'll never get it to give you back the same thing and start over again. And this is an example of what's called a strange attractor, because the attractor is a set of points that it can visit, and there are points that it won't visit. But that set of points is infinite, and it never repeats. So it will just continue giving you different numbers, which is kind of an amazing thing if you think about that. So let's stop there. I'm sorry that I didn't. I should have included one other graph there in between the 2.81 and 3.9 to show that there are, for instance, situations where the attractor is 2 points. It oscillates back and forth between 2 exact points, and then 4 points, and then 8 points, etc. We're going to talk about this so-called period doubling route to chaos, and that'll be about it for today. So let me stop there, stare again, see if there's any comments or questions on those graphs. Then we're going to open up a spreadsheet and look at it. Go ahead, Ben.
You're John, I'm Ben. It's a bit mathematical, but when you say these numbers will never repeat, a couple of questions about it. Do you literally mean, do you know anything about whether it's proven that the number sequences are all real numbers and that all the real numbers are different, and none of them rational numbers? And if they are real numbers, could that even be used as yet another proof of the existence of
God?
Uncountably infinite numbers and stuff. I don't want to get too into stuff like that, but
no, those are
it's
great.
A little bit interesting to me.
Those are great questions, and I don't know the answers to them. I do know that there is a really important number that comes out of this called the Feigenbaum constant, kind of a universal constant. And that Feigenbaum constant, I just learned yesterday, it's speculated that it's a transcendental number, but we don't even know for sure that it's irrational. It's a number that people are pretty sure has to be transcendental, but there's no proof that it isn't a rational number, right? That it isn't a fraction. And I think that is fascinating.
This constant, is this the one that starts with like 0.4 something?
No, it's something like 4.6, 4.7. And we'll talk about it before we finish today.
So you're saying it's known to be transcendental, but I thought a feature
No,
of transcendental
it's not.
It says
People think it's transcendental, but they've not
Oh, I
even
see.
proved that it's irrational.
Okay. Yeah, yeah. No, I was going to say, being irrational is a building block of being transcendental, right?
Yeah. No,
Yeah.
I think
Okay.
I think it's fascinating to have a number which is which is as bizarre. It has to be a very bizarre number, as the Feigenbaum is, but we don't even know if it's irrational. Speculated to be transcendental. Okay, for people who know what that means, I suppose maybe we can go into that. If yeah, well, we could go into that too. We can go into anything anybody wants to. But let's do the following. Oh, well, let me just ask: are there any more comments before we do go on? I want to open up the spreadsheet and do a few things. Okay, well, so if you open that spreadsheet on the next link, the first next slide, there's a link to a spreadsheet, and let me know. I kind of tested this out yesterday. I think everybody should be able to see it. And
I'm
let's
trying
see.
to click on laptop and it's not clicking. Okay, here it is. Okay, I'm there. I'm there.
Is
Yeah,
that
it's the
there?
permissions are set right, John. Yeah, you and I can edit it, but it's set for anyone with the link to see it. Yeah.
Okay. Good. And I think because you and I can edit it, I see a green box around the R that wouldn't otherwise be there, I think.
I had a cheeky fiddle, but I left it as I found it.
Yeah. Okay, good. So this is what I've got here. I should let me do this first of all. Let me change the R value. So what I've got here is just a little spreadsheet. It calculates, in fact, that column over at the right, at the left, sorry, that has iteration number and the ith value of x. I'm starting with zero point 0.2, and I've just now set r equal to 1.6, and that table goes on for 10,000 entries. I have 10,000 iterations extending down below there. And what you'll see just next to that is a graph that just shows the iteration values. You see it starts at zero point 0.2, and then it kind of climbs up very quickly levels off at, what is it, 0.375. Okay, I didn't realize I'd picked such a good R value. For an R value of 1.6, the fixed point is 0.375, 3/8. So an R value of 1.6 gives you an attracting value of 3/8. And that's what that shows there. Now I also have, just for future reference, just to the right of that graph that shows the iteration values, I have another graph that shows you the last 100 iterations of the 10,000 iterations that are in that table. And that'll come in useful in some particular cases there. So I'm hoping, let me know if anybody's having trouble seeing that on a phone. I don't know how well it works on a phone. I think it does work on a phone, but it's probably a little bit small.
If it's not working for people, I have it working on the YouTube
Oh, on
stream. So
YouTube.
you can click the link in the chat, and you can watch the thing happening in front of you if you're having trouble.
That's probably a really good thing. I'll just really recommend that for anybody especially if you're in the audience. You can just go to the YouTube and then you'll see them. Well, I suppose if you're on your phone, maybe it doesn't make that much difference. So anyway, do what's best. But Shamash has put the link to the YouTube in the chat. Okay, so anyway, 1.6, you see what happens, and it's coming to to exactly 0.375, it turns out. I'm just going to start gradually. Well, let me first of all show you what happens if r is equal to 0.9. If I put r equal 0.9, you see what I said there. It starts at 0.2, and it gets smaller and smaller and smaller and smaller. And what it does is it goes to 0. And it goes to 0 pretty quickly. But not I'm scrolling down and you can see by iteration 193, at least the spreadsheet's willing to call it basically 0, but it isn't 0 yet. It's still continuing to get smaller and smaller, but it just simply approaches 0. That's the fixed point. So let's go back to 1.6, and you see once again it climbing up to 3/8. Now I'm just gonna gradually increase. Here's 1.7, and you see it has the same character, but now it's increasing to a slightly larger value, about 0.41176477059. It seems to be the kind of fixed point in this case. And I'll continue. 1.8, it rises a little more. 1.9, it rises a little more. At 2, it very quickly goes to zero point 0.5. So with an R value of 2, this sequence converges very quickly to the fixed point of exactly 1/2. And it's important to kind of understand, to notice how quickly it's converging and how unquickly it converges in other cases. For instance, if I go to 2.1, once again now it converges pretty quickly, but it takes down to about iteration 11 to get to the point where the spreadsheet at least can't tell that things are changing. If I go to 2.2, notice it's still the same basic character, with one minor exception. It's converging a little less quickly. But anybody notice at 2.2 you get your first hint of something that wasn't happening before?
It starts going down. There's an inflection.
There's a what do you mean by that
Well,
exactly?
it used to be like uniformly increasing, and now after the third iteration, the actual limit is not above all the previous points. It's below like 0.4. I can't
Right.
really tell the value, but it looks like there's a bump now.
Right. It's a little, whereas up until this point, it just monotonically increased to the fixed point. Now it kind of it overshoots. Where is that? It overshoots in, which
I think
iteration
it's the
is
fourth.
that?
It's the fourth one. I think 0,
Well,
5,
I'll tell
5, 4, 5, 4, 6, and then it becomes 5, 4 again.
Okay. Okay. Yeah, I think you're right. Let's go to 2.3, and I think we'll see it a little more clearly. You see there that it goes up to 0.57 in the third iteration, but it's clearly settling down ultimately to 0.56 something. In fact, 0.56 to 0.565 to 173913, it looks like, is what it settles down to these many digits. I'm just gonna keep going though. So this is a new character. It's got this little oscillation thing around
There's also a dip
the
now.
front.
So we've seen the bump, and then there's a small dip,
Right,
and now we're seeing more of it here.
right. As soon as it overshoots, we're into a region where there is a little bit of an oscillation around. Once it gets up beyond there, it's oscillating a little bit. Let's go to 2.5. Oh, let's see. What just happened? Oh, I see. Okay. So that's interesting. I didn't even know that. That's interesting that 2.5 had that character. Let me put a new starting point in. Interesting. So see, you discover things all the time. With an R value of 2.5 and an initial X of zero point 0.2, it looks like the sequence is literally zero point 0.2, zero point 0.4, zero point 0.6, and then
Yeah,
it
but
just stays there.
I think you're just losing detail in the first few iterations because of that
Maybe.
starting
I
value.
don't actually I don't
Not
think so.
necessarily. No,
Maybe
not
not. I don't know.
necessarily.
But it's
If you, we have to resolve the equation, and then you will see, for example, 2 times 0.5 is 5 or whatever, and that is exactly the fixed point, something like that. It
Let
happens.
let me show you what happens if I start with 0.1999999. Right? So now we see that it is doing something like that, right? If I start with zero point 0.2 and I just change this to 2.499999, now, now we get different things again, right? So anyway, that's interesting. I don't know why I've never stumbled on that before. I don't think I generally start with zero point 0.2. I generally start with zero point 0.1. So that may be why I'd never noticed that before. You see that if I start with zero point 0.1, the sequence doesn't look particularly interesting. It just does that oscillatory thing around the final value of zero point 0.6, and it eventually gets to zero point 0.6. Okay, so that was interesting. I just learned something. 2.5, 2.6. It's going up. Still that oscillatory thing around. I'm gonna go back to starting at 0.2 anyway. So at R equal 2.6, it's still just oscillating around a fixed point. 2.7, 2.8. Notice at 2.8 now, the oscillation has gotten pretty wild at the beginning. It's taking a little longer to converge. 2.9. Wow, now it's really taking a long time to converge. And, eventually getting there, but the oscillations are pretty wild for a fairly long time. Rather than just jumping to 3, because I know what happens there, I'm going to go to 2.95. Notice now the oscillations are lasting almost out to the end of the first 100. There's still a little bit of up and down, even at 100. By the time I get to 2.99, it's not completely clear it's going to converge. So this might be a first time where it's worth looking at that little graph to the left, to the right of the main graph. That's 100 points, 10,000 iterations down. And you can see that if I do go out 10,000 iterations, it does look like it has finally converged to something. But it clearly took a long time to converge in this case. And if I go to 3, if I go to 3, you'll see that in the main graph, it almost looks like it has stopped converging completely. And if I go out to the last 100 points of the 10,000 iterations that I did, it's still not clear if that's converging or not. There's still an oscillation, an up and down oscillation. Once again, I don't know if you'll see that on a phone, but those points are just barely going up and down. So that's interesting. 3 looks to be something's happening at 3, and to really see what's happened at 3, let me just go to 3.1. At 3.1, you can see the oscillation now is still there, but it's clearly not converging, as is shown by looking at those 100 points, 10,000 points down the iteration. They're still at the same place they were at the end. So we're now in a place where the final state of this iteration is to go back and forth. It goes up and down. It hits the high value of like 0.76, and then it goes to a lower value. What is it? It's going like between 0.5, 0.7645, blah, 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 and 0.558014. If you look at here, even just 100 points down, it has converged completely to 8 or 9 digits. And it's just oscillating back and forth between those two values. So we seem to be in a... Yeah, go ahead.
Is there any guarantee, though, that it's just going to keep oscillating like this
Yes.
if we keep iterating?
Oh, yeah, that's easily seen if you examine the graph. Just do a little analysis on the graph. That part is clear. It is oscillating forever.
Maybe you can try to change the starting point here. So the initial
that's a good-
x0,
That's
and
a
then
good point.
for some values, it will converge.
Yeah, so look what happens if I start with 0. Zero is a fixed point, but it can't get to 0. 0 is a fixed point. If you put 0 into this equation, you're going to get 0 out. In fact, if you put 0 into this equation, no matter what value of r, you're going to get 0 out. So 0 is always a fixed point, but it's only for r values less than 1 that the sequence will go to 0. If you start at 0, it'll stay there, but it won't go to 0 unless r is less than 1. Does that make sense? So like, for instance, if I start at 0.0001, then it very quickly goes back to this oscillation, no matter what my starting point is. 0.9, 0.4, 0.2, 0.7. It always quickly approaches those same two numbers that it oscillates back and forth between. Okay, fun with math, right?
Presumably from above as well, if you put a large starting number in, like 1,000.
Well, if I put in 2, Notice what happens.
Yeah, beyond 2. Yeah, but 1.9. How about
If I put
1.99?
in, when you mean, so 1 point, how about I start with 1.01?
Okay. Same thing. So you really need a starting value 0 to 1. You're saying.
Right. And it's pretty easy to see why that
See that?
happens if
Yeah,
you just
from
look at the
the logistic
function.
math equation. Yeah, yeah.
Yeah, right. So you really do have
Yep.
to stay with starting points. You have to stay with x values between 0 and 1. But if I start with 0.99999, it very quickly. Oh, yeah, that's right. 0.999. Oh, that's interesting that it did that. It started with 0.999, went almost to 0, oscillated a little bit. I guess it didn't really oscillate. Came back up very quickly, goes to that same. But the attractor for all values for all initial x's except for 0 is that oscillating thing. So that's what happens at 3.1. Now let me show you what happens at 3.5. I'll do 3.2. There's 3.2. Let me start once again at 0.2. I'm just going to start at x equal 0.2. With r equal 3.2, it kind of immediately goes to oscillating between two values that are a little further apart. Let me just show you that again. Here's 3.1. Here's 3.2. Here's 3.3, a little further apart yet. Here's 3.4, a little further apart yet. Now look what happens when I just go to 3.5. Whoa. So now those two things that I had at 3.4 seem to have themselves both split into now two sequences. So now the series of numbers, rather than getting to a point where it's what we call period 2. It was period 2. It took 2 iterations to get back to the same number. Now it takes 4 iterations to get back to the same number. And it does one of the low numbers, then it does one of the high numbers, then it does a different low number, and then a different high number. It takes 4 iterations, but eventually I get back, as you can see in the last 100 points graph, it stabilizes out now at a period 4 cycle. And that's going to be characteristic of all values of the parameter between 3.44949 and 3.54409. You may notice the numbers that I haven't talked about up above the graph. Those are mostly just for my reference. But 3.3, the first number there, 3, is the place where it went from period 1 to period 2. Let me just show you. Here's 2.9, period 1. Here's 3.1. So 2.9 led me to a single point. Every iteration gives me the same thing. At 3.1, I'm in period 2 territory. It oscillates back and forth. It takes 2 iterations to get back to the same thing. And at 3.5 now, I'm in period 4 territory. It takes 4 cycles to get back to exactly the same point, eventually, when it has finally converged. And that's what those numbers represent. 3.44949 is the place where the period 2 becomes period 4. And 3.54409 is the place where period 4 becomes period 8. Let's see what happens if I put in 3.55. Notice what happens. Rather than getting 4 up like that, now I've got, and it's getting a little hard to see, but you can see that the 4 lines, each one of those 4 lines has now split into an oscillation between 2 values. And so it takes 8 full cycles to get back to the original number. If you think it's just a matter of convergence, look at the last 100 points and you'll see that it really is, even out there after 10,000 iterations, where it's taking 8 times one of the very low ones, then one of the low high ones, then the kind of high low one, and then the very high one, and then the other values in those. So it takes 8 full cycles. That was very poorly said. I'm sorry, I even wasted my breath on that. Anyway, it takes 8 cycles. This is where we're now in the period 8 region. And then period 8 becomes period 16 at 3.5644. So let me see. I don't think we're even going to be able to notice this. It starts getting really hard to see. If I put 3.566 in, I will be in the period 16 region. Now, maybe the best way to see that is for me to yeah. Let me do this. I'm gonna change this graph. I'm gonna make the maximum here 1,000. There. So by looking at the first 1,000 iterations in the main graph, can you see that there are kind of, there's 1, 2, 3, 4, 5, 6, 7, 8 lines of dots, but each one of those lines has a little bit of a back and forth oscillation in it. If you see, there's 8 lines, but each one has a little up and down oscillation in it. The 2 lines at the top are really hard to see that up down oscillation, but you can certainly see it in some of the other ones. And so we're now in what's called period 16. So let me just take a moment to point out that my PTR, if you look at my PTR in detail, you're looking at this behavior. You're seeing a fixed point. Now what this graph is showing you is the attractor as a function of R. So in my graph, why don't I have this one? I'll tell you what, let me do this very quickly. Oops, logistics map. There. I should have this image. Copy image. Paste into another sheet if I can here. I'll put it right here. So if you just look on, if you refresh and look on slide 4, you'll see a large version of the kind of thing I have in my PTR. And what this is showing you now is the fixed point as a function of R, not the fixed points, the attractor as a function of R. When R is less than 3, there's just one, the attractor is a single point. For R greater than 3 but less than 3.4 or whatever that was, there are 2 fixed points. You see you see that one fixed point splitting into 2, and then at 3.44 or something it splits into 4, and then at 3.5 something it splits into 8, and the splitting now happens more and more quickly with smaller amplitudes, so that you really can't even see in this graph what's happened there, what happens in going from 2 to 4 to 8 to 16. In fact, that period doubling, if you just follow that on, that's going to quickly get to 32, then 64, then 128, with the doublings coming faster and faster and faster until there's a place beyond which it has doubled an infinite number of times, at which point we're into what's called the chaotic region. The period is now doubled an infinite number of times, making the period infinite, meaning that the sequence will never repeat. This is what's called the period doubling route to chaos, and it's characteristic of an enormous number of physical systems. You can write mathematical equations like this and see it, but it happens in lots of physical situations, including driven pendulums, as we'll see. Well, actually, we won't see that, but you can see that as well. It's a fascinating feature, and it's a ubiquitous feature of nonlinear systems. So let me stop there. I've been yammering on for a while. Anybody want to make a comment or point to some other thing? I know we've got people
Now,
on stage who know about these things.
the
Go
pattern
ahead.
of these branching points is a bit interesting. I mean, you're quoting it to 5 decimal places, but what do we know about the
Yeah,
the
they're
pattern of
known.
these?
They're known extremely accurately, and I'm glad you asked that question, because that's really if there's a denouement today, it's really take a look at the spreadsheet there, and what you'll see up above the graph, if you look at the spreadsheet up above the graph, you see the numbers there. I already told you those numbers at the top, the 3, the 3.44949, the 3.54409, 3.5644073, etc. Those are the doubling places. So 3 is where it goes from 1 to 2. The next one is where it goes from 2 to 4. The next one's where it goes from 4 to 8. Those numbers are known to uh, enormous accuracy.
I believe the
And
first one, looking at the Wikipedia article, is 1 plus the square root of 6.
right, right. And
I'm just wondering if there's like a nice algebraic form for the rest of them, or
I think that the next one is known analytically. I think beyond that they're not known analytically, but I could be wrong about that. I could easily be wrong about that. But here's the
No,
really interesting. Yeah, go ahead. Go ahead first, and then I'll get to it.
most that I've seen are usually done in just pure decimal form. I haven't
Right.
even seen one of these ever done with a 1 plus square root of 5 over 2 or something.
but the
It,
first one is, so the 3.449 is 1 plus the square root of 6. I'm just reading that from the Wikipedia
Right.
article.
Right.
But
no, but you have it exact because
I think it is.
Yeah, that one is exact. And I think the next one, I think there's an analytical formula for the next one too, but I think that may be it. There may be, I think we know that they're all the solutions of
and that's for this map.
equations, but I
This
think they're
logistic
all
map you have
transcendental.
the with the t news 1 minus to times 1 minus to.
I'm sorry, say again. I'm not sure I'm not
The
sure I
logistic
understood.
map, the equation.
Yeah, this is for the logistic map. But here's the so let me just point to one thing that this is a universal feature, a semi-universal feature, I guess I should say. If you look at those period doublings, you notice they come more and more quickly. And in fact, if you take the ratio of the distance from one period doubling to the other, so you take you take the distance from one period doubling to the other, like the 3.44949 to the 3.5409, and you divide that distance by the distance to the next period doubling, you get the sequence of numbers that I show at the bottom there. In fact, that 4.75, the first number there in the bottom, is what you get if you divide 3.44949 minus 3, the distance from the first period doubling to the second, by the distance from the second period doubling to the third. That you get 4.75. And then if you do that for the ratio of the distance from the second to the third to the fourth, you get 4.656. And if you do it for the third to the fourth divided by the fourth to the fifth, you get 4.6683. And you notice that those numbers are very quickly converging to something like 0.4668. And that number that those things converge to is known to an enormous number of places, and it's called the Feigenbaum constant. It is the Feigenbaum constant is a semi-universal constant, a mathematical constant, kind of like Euler's number or anything else, like pi. And it's seen whenever you have these period doubling roots to chaos, you get this kind of behavior with that constant. So the Feigenbaum constant has kind of has taken its place alongside Euler's constant, pi, and other things. Maybe not as well known, maybe not as important in some ways, but another universal constant like this. And it was the thing I was talking about that it's speculated that number is a transcendental number, but we don't even know, there's no proof that it is even an irrational number. And in other words, there's no proof that the Feigenbaum constant isn't the ratio of two integers, which I just find completely fascinating. So that and because of the fact, of course, that that it is so large, Feigenbaum constant is large. That means that the distance from one period doubling to the next is going to be on the order of a fifth what the previous distance was. That means you very quickly double an infinite number of times, leading to the chaotic behavior that you see beyond that.
So the Feigenbaum constant is the distance between successive shrinkings, effectively.
Between successive period doublings. So you go from period one to period
depending whether
two.
you're going forward or backwards. Yeah, okay.
Right. Yeah.
Yeah, okay, I can see your formula there. And you're saying it converges to the Feigenbaum constant.
Right. And the mathematics behind this is people have the amount of effort that's been put into analyzing, getting as much stuff as you can analytically out of it is really remarkable. The Wikipedia article will give you a taste of just how detailed it is, but just a taste. Whole books have been written on these things.
I've had a look, and it doesn't look like we know anything but 1 plus square root of 6 as analytically, as far as I can see. I had a fair search and can't see that anything else is known, but you may know differently.
Well, I don't know differently. I was only thinking that yesterday I saw somewhere that the next value was at least the solution of a known equation. I mean, and maybe that's it. It may be known that those numbers are transcendental. If some of them are, I don't know. No reason really to think so, since the first couple aren't. But all right. So I'm kind of done, except I thought maybe it might be fun to listen to a little of the Veritasium. I thought I would just play a little of the Veritasium thing with what I've talked about. It might be kind of interesting. And if you want, we could both kind of, we could all kind of sync up on the beginning of that Veritasium thing, and then I can play it. Oops. Oh dear, there we are. Oh, there, okay. So I'm going to, if you want to bring up the video and maybe turn your
Are you going to
sound
stream
down.
audio, John?
The logistic map, the Veritasium, the second link on my fourth slide.
Yeah,
If you,
but if you're going to run the video, are you going to stream the audio or should I do it?
let's see, that's a good, I think, let me do it, I guess. I'm not sure what that means for you. You're going to be
Oh,
streaming.
nothing, not at all. I'll just
Okay.
open the video and mute it, and then we can get the audio from you.
Okay. And you don't have to, it's only if you want to see the visuals. I think it's worth seeing the visuals, but I'm not going to play the whole thing here. It's 18 minutes, but I'll play a little bit of what Derek has to say about the stuff that we've been talking about as well. Okay, in 5 seconds, I'm going to start my video. 3, 2, 1.
What's the connection between a dripping faucet, the Mandelbrot set, a population of rabbits, thermal convection in a fluid, and the firing of neurons in your brain? It's this one simple equation. This video is sponsored by Fast Hosts, who are offering UK viewers the chance to win a trip to South by Southwest if they can answer my question at the end of this video, so stay tuned for that. Let's say you want to model a population of rabbits. If you have X rabbits this year, how many rabbits will you have next year? Well, the simplest model I can imagine is where we just multiply by some number, the growth rate R, which could be, say, 2, and this would mean the population would double every year. And the problem with that is it means the number of rabbits would grow exponentially forever. So I can add the term 1 minus x to represent the constraints of the environment. And here I'm imagining the population X is a percentage of the theoretical maximum. So it goes from 0 to 1. And as it approaches that maximum, then this term goes to 0. And that constrains the population. So this is the logistic map. Xn plus 1 is the population next year, and Xn is the population this year. And if you graph the population next year versus the population this year, you see it is just an inverted parabola. It's the simplest equation you can make that has a negative feedback loop. The bigger the population gets over here, the smaller it'll be the following year. So let's try an example. Let's say we're dealing with a particularly active group of rabbits. So R equals 2.6. And then let's pick a starting population of 40% of the maximum, so 0.4, and then times 1 minus 0.4, and we get 0.624. Okay, so the population increased in the first year. But what we're really interested in is the long-term behavior of this population. So we can put this population back into the equation. And to speed things up, you can actually type 2.6 times answer times 1 minus answer, get 0.61. So the population dropped a little. Hit it again, 0.619, 0.613, 0.617, 0.615, 0.616, 0.615. And if I keep hitting enter here, you see that the population doesn't really change. It has stabilized, which matches what we see in the wild. Populations often remain the same as long as births and deaths are balanced. Now, I want to make a graph of this iteration. You can see here that it's reached an equilibrium value of 0.615. Now, what would happen if I changed the initial population? I'm just going to move this slider here, and what you see is the first few years change, but the equilibrium population remains the same. So we can basically ignore the initial population. So what I'm really interested in is how does this equilibrium population vary depending on R rate? Well, as you can see, if I lower the growth rate, the equilibrium population decreases. That makes sense. And in fact, if R goes below 1, well then the population drops and eventually goes extinct. So what I want to do is make another graph where on the x-axis I have R, the growth rate, and on the y-axis I'm plotting the equilibrium population, the population you get after many, many, many generations. Okay, for low values of R, we see the populations always go extinct, so the equilibrium value is 0. But once R hits 1, the population stabilizes onto a constant value. And the higher R is, the higher the equilibrium population. So far, so good. But now comes the weird part. Once R passes 3, the graph splits in 2. Why? What's happening? Well, no matter how many times you iterate the equation, it never settles onto a single constant value. Instead, it oscillates back and forth between two values. One year the population is higher, the next year lower, and then the cycle repeats. The cyclic nature of populations is observed in nature too. One year there might be more rabbits, and then fewer the next year, and more again the year after. As R continues to increase, the fork spreads apart, and then each one splits again. Now, instead of oscillating back and forth between two values, populations go through a 4-year cycle before repeating. Since the length of the cycle or period has doubled, these are known as period doubling bifurcations. And as R increases further, there are more period doubling bifurcations. They come faster and faster, leading to cycles of 8, 16, 32, 64, and then at R equals 3.57, chaos. The population never settles down at all. It bounces around as if at random. In fact, this equation provided one of the first methods of generating random numbers on computers. It was a way to get something unpredictable from a deterministic machine. There is no pattern here, no repeating. Of course,
Sorry, I didn't mean to do that, but I think it's a good place to stop for at least for a
did know
moment.
the exact initial
Whoops,
conditions.
sorry. There. Yeah, so you heard, maybe I hope kind of saw, that was pretty visual. He was not, he knew he wasn't talking to a vision impaired audience like I am here. But anyway, I'm going to stop. I'm going to stop there for now. We can go back and look at more of that if anybody wants to. Let me just see if yeah, and I guess the only other thing I would like to show you is the chaotic pendulum thing on this link. But any comments or questions on that? We were going over pretty much. He was going over pretty much the same thing we did. That's a nice video to watch maybe later on if you want. Well, if there's no
Yeah,
comments, let me.
I've seen
Yeah,
this
go ahead.
video.
Go ahead, Sam.
I don't know. Yeah, it's just I've seen this video.
Yeah, it's pretty good. So this kind of thing occurs in actual physical systems as well. It requires these kinds of behaviors require systems that are so-called nonlinear. They have to be such that the differential equations that describe them are nonlinear differential equations. And one of the simplest nonlinear differential equations is the one that describes the motion of a pendulum. Because a pendulum, it turns out that the restoring force on a pendulum depends on the sine of the angle by which it's displaced from its minimum point. And that sine is a nonlinear function, which makes the pendulum inherently a nonlinear thing. Now, just because it's nonlinear doesn't mean that it does all these crazy things, but it does turn out that in systems like this, in actual physical dynamical systems, you get very interesting behaviors when you have a periodic driving force and some kind of damping for reasons that are very deeply embedded in the ideas of Hamiltonian phase space and et cetera, if you've ever heard of any of those kinds of things. But the net result of this is that if you drive a pendulum that is simultaneously being driven, so you drive it kind of sinusoidally, you just drive it periodically, and it's also being damped, then a pendulum can do these same kinds of things. It can settle into a cycle, a one driving period cycle, but it can also at certain values of the frequencies or the amplitudes of the driving force, it can settle into a period two. It'll do one thing through one cycle of the driving force, and then a different thing through the next cycle, and then it'll repeat exactly. So it'll go kind of back and forth, back and forth, back and forth, back and forth, back. That's kind of a period two type oscillation. And then it can go to period four, period eight, period 16. And those doublings come quicker and quicker, a Feigenbaum constant kind of a thing. And they then go into chaos, where the pendulum itself will never repeat the motion, no matter how long you wait. Now, in reality, that never happens, because in reality, you can't ever get anything to be as precise as you can mathematically. Like all the things we've been talking about are pure math, just analyzing the results of this purely mathematical system. But as soon as you actually try to do something in the real world, noise, uncertainties, etc., come into play that make some of these behaviors pretty hard to see. So let me just take you to the last link. If you just open up that last link, the chaotic pendulum link. I'm showing it on the YouTube, I guess. Oh, why am I? No, I'm not. That's right. I always forget what I'm showing. If Shamash opens up, he'll be showing it there. It opens up showing you a swinging pendulum, and you'll notice that this pendulum is able to swing all the way over the top. If you open that up, you'll see it's not constrained by any kind of thing that would keep it from going over the top. And there's also shown on there a driving force that oscillates back and forth one way, then the other. So the pendulum can even sometimes go all the way over the top and then be driven back the other way if the force is big enough. On the side, in the opening display is what's called a phase space diagram for this thing. It shows on the x-axis, it shows the angle of the pendulum, and on the y-axis, it shows the angular velocity of the pendulum. So when the pendulum is moving, I guess when it's moving in the counterclockwise direction, it's considered to have a positive velocity. When it's moving in the clockwise direction, it's considered to have a negative velocity. And the graph simply has a little red dot that moves along showing the current angle and the current angular velocity. It's a little, it's if you're looking at that, you'll also have to notice that it has what's called periodic boundary conditions, because the angle of the pendulum can go through more than one full cycle. Or it can go around and around and around and around. But every time it does go over the top, the phase space diagram just goes over to the other side. It considers an angle of over the top plus 10 degrees. It just considers to be 10 degrees again, if you want. I didn't say that very well either. And I don't want to spend too much time on this, but if you this thing is opening up in a particular part of parameter space, as it's called, I believe that is chaotic. If you explore it, it's a fun website to explore, and I won't do it because I'll have to talk you through too much stuff. You can look at different displays. You can set parameters that are in a period. Maybe I'll just do that. If you just scroll down a little bit, you'll see that it has some preset conditions, and one of them is double loop. If you find double loop and just click on it, you can go back and watch the result. And you'll see that now what it's doing is something that takes 2 cycles to repeat, I believe. Let's see if that's really true. No, that doesn't seem to be true. Oh, maybe it has to settle down. I think maybe it has to settle down. That's right. So it needs to damp into this double loop. So if you watch that, if you click on the double loop and watch it for a while, you'll notice that it eventually settles into a pattern where it comes down, goes over the top clockwise, stops near the bottom, goes up a little bit, counterclockwise, then it continues clockwise, goes over the top again, stops near the bottom, goes back up a little bit, comes back down, goes over the top again. And it'll take a while to settle down, but the pattern is very much like what we saw in the logistic map, in that it's now, when it settles down, it will be in a strict 2 cycle of the driving force pattern that repeats over and over again. And he's got another set of parameters there for period 4, etc. Enough said. I don't want to spend any more time on it. If you look at things like this, you can find lots of things like this on the web. They're kind of fun to watch. And enough said. I think I'm done. We can talk about this. We can talk. I hadn't really intended to talk about anything today. I thought we would just kind of do what Ben did last week, which was, I thought, really fascinating too. We got in. What did we talk about last week, Ben? It was really good as it ended up.
It was that fascinating. You know what? I've temporarily forgotten as well, but I'm sure somebody else will remember. We ended up talking about encoding and error correction.
Oh, right. Yeah.
And that sort of stuff in the end.
I thought that was really, really good. And you hadn't picked that as the topic. It just migrated there.
Yeah, indeed.
So it'd be lovely to do the same thing. But if anybody wants to talk about anything more here or have any other comments, let's go for it. Oh, we've got Bert on stage now. Bert, I don't know if you came up to say something or just hang with the cool kids.
Oh, definitely hang with the cool kids. But I had fun yesterday. I just happened to pop open Flight Radar 24, and I watched a flight that came from Santiago to Sydney.
Oh yeah, I do that all the time.
Mm-hmm. It's like sometimes they're they take what would be the direct Great Circle route. This one, and I assume is due to where the jet stream was that day and such like this, dipped way south,
Over
um,
Antarctica?
and it came within 50 kilometers of Antarctica.
Wow.
Yeah, so it actually left Santiago, went almost directly south down the Pacific coast. So the Andes Mountains would be on the left, and the South American coastline, and then cut across the southern South Pacific. So it's kind of like taking a guitar string and stretching it to one side. If you look at instead of the
Yeah.
great circle chord, it's like kind of going off the side a little bit and then back. And then look at my PTR. It came up almost going directly north, went over
Yeah.
Tasmania, and then landed at Sydney. And for fun, I put that onto a flat Earth map, and we were talking about it. This is in Ten's room,
Uh-huh.
and well, how do you know that's really where they went?
Yeah, I know Rohan. I don't know how many people here follow along in these things, but Rohan once purchased a ticket on that flight just to show that you could. But then of course didn't actually he didn't take the flight, and so they accused him of wimping out because maybe the story with that flight is that it doesn't exist because it can't exist on the flat
Right,
Earth.
right. So in my PTR, there it is, the actual flight path
Yeah,
that it took.
I think every day basically it takes off to the south and
Not
arrives from
usually
the north.
that directly
Not
south.
as directly, right?
Right, it goes more southwest.
Yeah.
And so then let me pin this, set this profile. Okay. And now take a look at my new PTR. There it is on the full AE map.
Yeah.
And in just 14 hours.
Now, how did you just you must have eyeballed that
Yeah.
point by
Yeah.
point on yeah, right.
Yeah.
I
There,
keep wishing that there was some online thing that would directly translate any path onto the AE map. That would be kind of fun.
I'm surprised it doesn't exist already.
It seems like there should be something like that. I'm a little surprised that that flight would do that. Well, I guess we are. We're on the other side of the equinox, aren't we? We're approaching summer down there. I guess I would think that would be very
Bert, it's even
unusual
more exaggerated than
in
that
June
because
or
it's not coming
July.
up through Tasmania. Look at that.
You're
You're
right.
not even you went around to New Zealand. You're not even close to the extreme.
You're correct because when I drew that, it was still 4 hours away from landing, or 3 hours away, and so yeah, I didn't get the actual path over Tasmania in that
It won't
drawing.
make a difference to the flat earthers, but yeah, I
No,
mean,
no, yeah,
nobody would fact check a
right.
false claim, right?
Yeah, it's an amazing flight. I remember the first time I looked at it, I was thinking, I mean, I just looked at it, I was thinking, wow, I wonder if that does go over Antarctica. And of course, normally it stays pretty far away. I think probably several hundred miles at least,
Yeah,
maybe 500.
here's the Great Circle map I just put in my PTR.
Mm-hmm. Yeah, so that's probably more like 1,000 almost, huh? 500 of 1,000 probably.
I don't know if it's that much actually. Let's see, where are we at here? Yeah, maybe 500-600
Looks like.
miles.
Yeah, okay.
Yeah, so the fact that it went south down the South American coastline, if you follow that and then cut over, it skimmed past both sides of the big bay of Antarctica, right? Like the 2 points that are most farthest
Mm-hmm.
towards the red line, and then cut north, went right across Tasmania, which you see in the map there too. I would have definitely paid money to be on that flight
Yeah.
because they would have seen Antarctica out the window, as
Yeah,
well as beautiful views of the Andes and flying over Tasmania.
But just the ice wall part of it, they wouldn't have seen.
Actually, you see, I'm sure you see ice flotilla ice all around there too and
Yeah,
everything.
but I mean, because they can't see the other side, they're gonna call it a wall, right?
Mm-hmm. Well, from 39,000 feet, you would maybe.
It's fun to look at what that flight. I mean, well, so first of all, I mean, here we are. So one of my favorite topics. I hate to admit it, but I do love talking about flat Earth related things. On the now kind of discarded. I mean, a lot of the flat earthers are moving away from the only map that makes any sense, the so-called Gleason map, this azimuthal equidistant map centered on the North Pole. You look at that flight on that map, and it goes up along the coast well, it actually goes up through South America, across the Gulf of Mexico into the United States, out somewhere in the Northwest, through the Gulf of Alaska, down along Japan, China, and eventually into Sydney. Basically, it's a polar flight. It's just the North Pole that it goes to. It's chaos, I tell you. Nonlinear is all get out. Yeah. So anyway, I might expand this a little bit. I'll kind of see what we can do about talking about some actual physical systems. Maybe I'll just mention one of and Andy knows about this because he went to Santa Cruz and hung out. Well, I don't know, hung out, but I'm sure met some of the people that did these dripping water experiments. It turns out that if you have a dripping faucet and you can control the flow of water to the faucet just really finely, you can see a period doubling route to chaos in a dripping faucet. In that some rate of flow, it'll go drip, 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 drip. And then if you turn up the flow a little bit, at some point it'll go drip, 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 drip. And then you turn it up a little bit more. And if you're really lucky, you might get a drip, 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 kind of a period 4 dripping. I don't think anybody has ever managed to get period 8 drips, because it's just, number one, the range of flow that you have to be able to control is now getting really tiny, and just all of the noise in the system makes it hard to do. But it's fun to understand. Maybe we just ask, what do you think causes that? How does a dripping faucet? What's the dynamics of a dripping faucet that makes it do anything other than drip, 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 drip?
It's listening to prog music and keeps changing the time signature.
That could be it, but no, that's not the answer. Anybody have any ideas? It's really interesting.
It should have to do with the hydrogen bonds that are in the water. So with a little bit more water, one drop will drag its partner, but then it has to wait for the other two to drop. And I'm guessing, I don't know.
Well, there's a lot of stuff you just said there that's pretty good. I don't think you quite nailed it, but it's definitely, it's not really so much about the hydrogen bonds, except for the fact that, all of that stuff is implicated in surface tension. Surface tension's important. Dripping faucets definitely depend on surface tension. When a drip leaves a faucet, it basically separates from what is the forming next drip, right? It's not like it leaves the faucet dry. It leaves the faucet with a little hanging dab of water. And that hanging dab of water is going to be given a little bit of motion by the separation. The separation is going to make that little drop kind of oscillate a little bit, right? And then the time that it falls can be affected by the oscillation that it's left with if it's if it's quick enough that that oscillation is still there. So you got a little hanging drip that's kind of going boom 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 while it's growing, and the time that it actually separates is going to be affected by the fact that it's kind of going boom 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 boom, and then it leaves the next drop with some kind of a little if you know what I mean. God, this is
I
where
know
you
what you
really need
mean.
But
visuals.
wait, but the thing is that you go doop 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 doop, right? If 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 the second drop also exerted the same uh effect, then you would see just the periods getting faster.
Well, not faster, but not changing, right? That period for the next drop would be the same as the period. I mean, the time for the next drop presumably would be the same as it was for the previous
Okay,
drop, right? And that's
So
right.
the
And
but
that's what typically happens, and
but
or the oscillation just isn't enough to make a
but when you go
difference.
to the second one, the deep 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 deep, so how come the second one
Right.
doesn't do the same thing for the third one? The
ah
What?
third one just goes back to the original.
Right. Yeah, good
the
question. What do you think, Bert?
I was gonna say then the water is depleted in the drip area of the faucet. So it's interesting if you plotted the flow of water and counted it per drips, right? Um, it's almost like the time required for a drip to form and fall versus the flow rate of number of drips to the end of the faucet, right? If you count in drips per second or whatever, um, it builds up enough that the first drip falls, releases the kind of, as you say, the wong wong wong, the shock wave, so to say, of it departing, and there's enough water there that it breaks the next drip free, but there's not enough water yet to form the next drip. So like the second drip gets broken off prematurely, so to say.
Right. Yeah. So you can think it may not be obvious that this happens. I mean, it's not obvious maybe how it could happen, but in the period two region, the first drop leaves the second drop leaves the forming drop in a certain state that causes it to fall at some point, and then when that drop falls, it leaves the drop. It leaves the forming drop in a different state, but a different state that's pretty much exactly the same as it will be two drops from now, right? When you're in a period one kind of a thing, each drop leaves the forming drop in the same state. But when you're in the period two, each drop leaves the forming drop in a different state, and so
Right.
and you
There has to be enough water buildup for a drop, and if it's coming in fast enough that it builds up more than the drop needs before the drop releases, then the little shock wave of letting it go pre-releases the second drop.
yeah
So
the
is the second drop smaller than the first drop?
I
Oh, interesting.
Yeah, so I think it's probably always the case in period two. I would guess that well, and whenever you're in anything other than period one, my guess would be that yeah, there would be a detectable or a meaningful difference in the size of the drops as well. I think that's probably right. The thing that
I mean, the
people
size of a droplet is determinable. So it is predictable based on temperature and pressure, what the size of the drop is going to be. So
Mm.
so
not
basically, if you're saying it drops premature, it means that the drop is smaller. The size is not the standard size at that temperature and pressure. So so now you don't have a thermodynamically stable drop the thermodynamically stable one would have been the bigger size.
Well,
So therefore,
I guess I'm not sure, Sam, I don't really see how you could predict and why really
based on the surface tension at
mm,
that temperature and pressure,
I guess
you can determine the volume that that would give you that surface tension.
well, I maybe. I mean, I think in principle that's probably true, but I think another factor is the detail shape of the faucet itself, right? If it's got a little bump, there's going to be if it has a little bump on the rim of the faucet, that bump is going to be a place that it kind of preferentially drops from, depending on how sharp that bump is. The size of the drop might be different. I mean, I think there's lots of things that affect the size of the drop ultimately, other than just surface tension and pressure and volume. Or pressure and, well, volume, I guess, does determine it. But you know what I mean?
Yeah, but see, the thing is that I mean, I'm going by an IV drip, right?
Mm-hmm.
There, you determine the flow rate by the rate of drops.
Mm-hmm.
And you can do that because all the drops have the exact same size.
Well, you say exact, but I think
Well, I
think
mean,
you're
within the error of, the thing.
right. In an IV drip, nobody cares to get it closer than 10-20% of what you're looking for, right? In an experiment like this, you're going to have to be able to control that flow rate at an incredibly minute
Okay.
level.
All right. Yeah. I
Yeah,
buy that. I buy
yeah.
that.
And that's one of the things. I actually have a colleague who did do this, reproduced it, and I think did just about as well as the Santa Cruz guys did. Certainly got up to period 4. Could actually detect period 4. I don't think he got period 8. I don't know if the Santa Cruz guys ever did. They might have. Maybe Andy knows. I don't know if Andy has ever actually looked at that. But it's really hard. I mean, you just kind of you're really happy if you see, period 1 to period 2, and then period 2 to period 4 being, maybe 3 or 4 times or 5 times as fast. If you can detect anything like that, you've done a really impressive job of controlling your experimental parameters. But fundamentally, the interesting thing about it is that I mean, my sense is kind of that, you get drip, 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 drip. But when you start leaving the next drip in a different state, it almost seems, I mean, I guess the thing my mind leaps to is you're kind of immediately now in chaos. But for some reason, that's not what happens. First thing that happens is the first drop leaves the second drop in one state. That second drop leaves it back in the state that the first drop needed. And it's interesting that it should do that. To me, it's interesting that would be the first thing that happens. I don't even know if I'm explaining that very well. Well, anyway, I'm satisfied to close down the room. We can do actually, I need to do some work, so I'm not going to be doing an after party today. But maybe I'll just put it that way. Somebody wants to open an after party or continue the discussion, that would be great. I may join in, but I'm going to have to be busy with a few. I have another gig tonight and a set list of things that I haven't played for a long time, so I have to do that. And I have honeydew or things to do. So I'm going to start heading toward closing down. Any other comments before we close down? Oh, I drove Benjamin away. We don't have him to torment.
Yeah, because you don't have any data. This is just pure mathematics as usual. Like, when do you ever have data, John?
I'm not a data guy.
Nobody has the data. It's all fake.
I asked them, I read all of Clauser's papers, and so I even more so than ever don't know what you're talking about because the data's there. And he said that his point is that no one has independently verified the data. I'm like, no, that is not your point. Your point has always been that they didn't submit any data, right?
Oh, come
That
on,
was
Sam, you're not
Claire's
that
law.
naive. Come
Claire's
on,
law
Sam, we
wasn't
all know
that
it's fake. It's
independent
fake. Don't believe it.
verification.
The earth is flat. Don't believe it. It's fake. Don't believe everything you read. Come on.
So has he read Clauser's papers? I don't know.
Yeah, I don't. That's a good question. I know that I haven't. It's interesting, to
John,
me.
John, 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 we're doing it again. He's not even here and we're talking about this. But we're
Right.
doing it again.
Well, I did want to say this one thing, which I think
Conversation.
is really interesting about, for those of you who haven't followed this as closely, John Clauser did the first experiment on quantum entanglement. And it was done back in the early 70s up at Berkeley. Is that right? 70s, yeah, right.
The first, so starting in 72, he comes up with papers on proposed experiments. In 76 is the first paper with
Ah,
actual experimental data.
okay, good. So yeah, and it's interesting. I was walking around in the same building that he was doing that in, and I didn't knew nothing about it at the time. But the interesting thing about it is that Clauser did this experiment on quantum entanglement. It was motivated by a thing that John Bell had written, by Bell's theorem, showing that, which was an answer to Einstein. Einstein had proposed that quantum mechanics has to be incomplete because it wasn't able to make predictions of the real properties of some real properties at the same time. You couldn't, it made the prediction, let's put it this way, it made the prediction that some properties of objects literally did not exist until they were measured. The only thing you knew was the probability of the measurements, and those probabilities did not reflect a lack of knowledge about the system. It was literally the case that the system didn't have a well-defined property until it's measured. And Einstein didn't like that. Benjamin doesn't like that. Einstein wrote a very compelling paper explaining that even though quantum mechanics doesn't tell you the value, it certainly must exist. This is where the idea of hidden variables, if you've heard, comes from. And then John Bell wrote a paper showing that, in fact, quantum mechanics makes predictions that cannot be explained in the way Einstein demanded that they be explained. Bell's paper showed that quantum mechanics makes predictions that cannot be explained that way. So your only choice is to believe that quantum mechanics is just wrong, which would have been at that point kind of hard to imagine because it had been so successful that it would be wrong in this one case. Say that, what's your choice? Yeah, your choice is that it's wrong, or that you abandon the idea that Einstein had of real values for properties that hadn't been measured. And the question is what Einstein would have thought if he had known about that. He wasn't alive when that happened. But Clauser did an experiment to see if these predictions of quantum mechanics were correct. And people dissuaded him from doing that, said, don't waste your time doing this. You're going to look like a crackpot doing this. Everybody knows what the result is going to be. And Clauser did the experiment, and he got the result that everybody knew he was going to get. He was disappointed, I think. I think it's fair to say he was disappointed because he was hoping that he would show that quantum mechanics was wrong. He certainly would have gotten the Nobel Prize had he done that. Did the experiment, got the result everybody expected, and 50 years later, he got the Nobel Prize for having done that experiment and getting the result that everybody knew he would get, which I think is kind of an amazing story. the intervening period saw some new ideas about and it saw the rise of people wondering what quantum mechanics is really telling us, and it led to other experiments and so on. So he got the Nobel Prize basically for being the first person to do such an experiment. But it's just, I think to me, it's fascinating that he gets the Nobel Prize for doing an experiment, getting a result that everybody knew he was going to get, and that disappointed him because he thought if he'd gotten the other result, he would have gotten the Nobel Prize, which he would. In fact, he would have gotten the Nobel Prize no matter how that experiment worked out. That's what's really interesting.
So anyway, if you want to read his papers, just Google his name, and then you see johnclouser.com. If you go there, the PDFs of all of his papers are on that site.
I need to do that. Have you looked at them? You've just
Yeah,
seen
I
them.
read, I mean, I didn't read the 2000s ones because they were mainly reviews or book chapters, but and then the 72 ones because they were proposed experiments. I didn't read those. I read the 2 or 3 after this, starting the 76 one, which is the big one, and then a few after that. He then, in subsequent papers, he treats other people's data to his calculation and says that it comes out as he predicts.
Well, that's really interesting. I'm gonna,
Yeah.
you have to spend some time with that. All right. So one last time. Oh, we got who we got? We got 10 on the stage. We got Benjamin
I'm
on the
back.
stage.
I'm back here. Sorry. I just have, I saw Hanson showed up and I wanted to make sure I got to give Hanson some links. Here's a video of Roger Penrose saying quantum theory as a whole is wrong. Just leave that there for.
Is that the one we went over yesterday?
No, it's a different one.
Is it? But this is the one maybe we looked at 6 months ago or something.
Could be.
Yeah.
So which part of the which part of quantum theory is wrong? Which part?
All of it.
He's saying all of it.
You can't
Yeah.
pick
Well,
and
that's a good
choose.
question.
When
What would
something's
you?
wrong, it's all wrong, right?
Yeah. But I wonder what Benjamin's answer. I shouldn't have leapt in. Benjamin, what would your answer to 10 be?
I mean, Ken is asking about Roger Penrose specifically.
Yeah.
Well, Roger Penrose, first of all, he thinks that the observation problem, the measurement problem, the observation problem is what he focuses on mostly. He thinks that's just a ridiculous proposition. Completely, he's making jokes of it. He's making Schrodinger's cat look like a silly little meme. He's using a lot of time to ridicule the measurement conscious observer measurement problem.
Right. What do you think he'd say about quantum entanglement?
It's difficult to answer because he doesn't speak to it directly very often. He's so uncomfortable with the bifurcation, the idea that all the world behaves like quantum until you get to a measurement or an observer, and then suddenly it isn't quantum anymore. Like that's a cuckoo crazy idea, right? The collapse of the wave function is cuckoo crazy. But he also says that it exists, and he says that it is done in physics, right? It's not done by the observer. It's not a process of measurement, consciousness, or anything like that. It happens in physics. So he says that it collapses.
John,
He
just
says that it
very
happens.
briefly, but before you continue to entertain this stuff, I'm just going to disappear. But you did say, did anybody want to say anything? I did want to say thank you for taking your time to run the room. So thanks, mate. And I'm gonna disappear and let you.
All right. Thanks, Ben.
Right, see ya.
Always
Good
glad
to
to
see you,
have you
Ben.
here. Yeah. Thank
Cheers,
you.
Ben.
Thank
So
you.
pitchy to me, all of it. I don't. What kind of nonsense is that?
John, should we move to the after party so the YouTube and the recording doesn't
Oh,
get.
that's probably a good idea. Yeah, let's do that, and I'll hang around for a little bit because I am kind of interested in this in this
Good.
conversation.
Yeah, I'll go ahead and open up the after party and you guys can come
All
over.
right. Yeah,
Cool.
good.